స్టార్ట్ అయింది.
Good afternoon everyone. I hope all you had a refreshing lunch break. We shall now begin the second technical session of day 5. Our resource person for this session is Dr. Lavanya Maddisetti, Senior Analog Design Engineer, Synapsys India Private Limited. She will deliver a session on from FinFET technology to SOC design, device parameters, design methodologies and AI for next generation chip design. It's my pleasure to introduce our distinguished speaker for this afternoon session, Dr. Lavanya ma'am. She is Senior Analog Design Engineer at Synapsys India Private Limited, specializing in VLSI circuit design. She obtained her doctoral degree from KL University, where her research focused on integrating machine learning algorithms into VLSI circuit design methodologies. She has authored more than 15 research publications in leading international journals and conferences. Her research interests include machine learning for VLSI circuits, technology node migration, circuit optimization, and scientific machine learning for next generation chip design. Ma'am, we are delighted to have you with us today. On behalf of Vardhaman College of Engineering, I extend a warm welcome and request you to kindly deliver your session, ma'am. Please, ma'am. Then you can keep this is on the off. This is on the off now. Red button. Long press. It's off actually. We can keep press give it a button. And this is for YouTube link. You get
Good afternoon everyone. Is my voice clear? Yes? Okay. Good afternoon everyone. Thanks for EC department and Electricity department for I'm Lavanya. I work for Synopsys. Generally my work there in Synopsys is on technology migration, that is migrating from one techno to the other techno, and also working on blocks, that means circuits. That is what is my work in Synopsys. So today's session, it is on FinFET. Generally we work on FinFET technologies, and after that recently, from past 2 years we are working on gate all around technology. So we will see what FinFET and gate all around technology is in brief in this session, right? So this is the topic that we are going to what is FinFET and and why it has feature, what is the reason behind that. So some of the topics we might see, you might feel that you know them, but in order to understand exactly is FinFET and why we are going for FinFET, we need to understand what is the drawback or what are the limitations of planar MOSFET. Okay, let us see. This is the outline of today's topic, where I'll be starting with the planar MOSFET, limitations of planar MOSFET, FinFET technology, the fundamentals, which includes the parameters and how the FinFET MOSFETs or FinFET transistors are used in general circuits, and then we'll go for advanced nodes than FinFETs, which are gate all around technology, and then FinFET to AI driven design. So coming to the introduction, so what is the necessity to go to FinFET? From almost around 40 years we worked on planar MOSFETs. So what is the need to go to the FinFET? Why, what driven us or what driven industry to go to the FinFET is, if you see the technology evolution, all these statements you might be knowing. The reason why I kept here is just to have the continuation from planar MOSFET to the FinFET. So if you see the technology evolution, we are using, we started using semiconductor technology from 1960s around. Now we are in 2020s, where industry is using gate all around technology. So we will see what it is. So in the future we will have CFETs. So you might have seen all these views, cross-sectional views, MOSFETs in all the textbooks, right? Do you see any disadvantage, or did you notice any disadvantage or the limitation with the planar MOSFET? You might have studied in second, third and fourth year syllabus, right? So what are the limitations that we have seen till now with planar MOSFET? It is advantageous. When we were in 90s, it was very good and we used it, and we have seen so many evolutions using MOSFETs also. But the important thing here is we want speed, right? If our mobile is not operating at with our expected pace, then we don't accept, right? So speed is the main criteria where we are interested in. So in order to accept or in order to get that speed, the planar MOSFET is not working according to our expectation. It is good. Planar MOSFET was working very well when the speed was not the criteria. But now it is not like that. We want everything to be fast. We don't have time to work or to give time for the MOSFET to run, right? So if you see, these are the advantages with planar MOSFET. But if we go less than 100 nanometers, let us suppose we have 45 nanometer in our college. So we are working with normal planar MOSFET and there is no issue, right? Now, even with planar MOS, we have seen that the disadvantages are short channel effects. Yes or no? There are short channel effects that are introduced in planar MOSFET. What is short channel effect? What's going on? If you take any MOSFET, what is the general expectation or general operation of the MOSFET? We want gate to be controlled. Gate should control the MOSFET, right? But what's happening? What is happening is the gate is not controlling the MOSFET, but drain has occupied the channel because of VDS voltage. The drain voltage is getting increased whereas the gate voltage, let us suppose it is remain as it is. Gate control, drain has taken the control, because of which what happened, the drain is entering into the channel and generally gate should pull the electrons from the substrate, but drain is doing that task, right? So because of that, these short channel effects are coming into picture. So the gate is losing control over the channel. That means whatever the expectation that we have with planar MOSFET, that expectation is lost because of drain. That's what is this figure which is at the right side, where drain has entered into the channel and the channel size is reduced. So these are the limitations of planar MOS. Short channel effects are the effects that are due to the decrease in the channel. Why the channel has decreased? Because of drain introduced or entered into the channel. So the limitations are leakage current, and the switching also is reducing. Ultimately, if the switching is reduced, the device performance also reduces, or it is not meeting according to our expectation. Okay. But what Moore's law says, for every 2 years the transistor should double, but it is not like that. It is, the number of transistors on the chip is going beyond double, because we want our expectation is not according to Moore's law. That is the reason now Moore's law is not working, right? So let us just briefly see what is short channel effects. Ultimately, whatever the short channel effects that I am showing here, the final concluded point is gate is taking control over the channel, drain is controlling the channel. That is the only point where all these short channel effects are coming into picture. Okay. So what is this threshold voltage roll off? See, if you see the operation of the MOSFET, if VGS is greater than the threshold voltage, then only the transistor starts on. Yes or no? Right? But because of the drain voltage, the threshold voltage also is getting decreased. That means as the technology is growing, the threshold voltage is decreasing. Right? That is what is threshold voltage roll off. That means it is decreasing. That is what is the graph shows. Okay? And drain induced barrier lowering is one of the short channel effect, where here, as I said, drain is occupying the channel. Generally, we want electrons will flow in the channel and current will flow due to electron movements. That's what is the operation, right? But because of entering the drain into the channel, electron flow decreases, right? And current also will decrease. Ultimately, leakage current increases. So if you see the drain versus threshold voltages, if you notice the left side, drain voltage, if it is 0.5, then if drain voltage is 0.5 and threshold voltage is 0.5, it was normal operation. It's like the expected operation of the planar MOSFET. But what is happening as the technology changes? Drain voltage is increasing, that means VDS voltage is increasing, the threshold voltage is remaining as it is. That means it is remaining as it is, or it is reducing. That means here we can notice that the drain is taking control over the channel. General expectation is gate should take the control over the channel, but it is not the case here. So that's what is the relation between drain versus threshold voltages now. Not now, before actually. Now it's more worst. So reduced gate control, that means gate is losing control over the channel. That's what is this slide says. Because gate is losing control, what I want to show here is, if you see this diagram, see the main disadvantage with the planar MOSFET is two points. You can directly, generally these 2 points are mentioned in any place, then that indicates that okay, these are the limitations or disadvantages with planar MOS. One is gate is losing its control, and if you see, we have source and drain diffusions where the channel is between source and drain, right? Now once if the gate is losing control over the channel and drain is taking over the control, then what happens? Current should have some space to flow. Yes or no? Current should flow and electrons will flow. Current also should flow according to the electron flow. So it chooses the other path, which is the lower part, that means substrate path. Okay. So because of that, we call it as leakage current. We want the current to flow in the channel between source and drain. That is what is the current that we require. But because of all these short channel effects, the current is choosing not the channel path. Why it is not choosing the channel path? Because it got reduced. Because of that, it is choosing the substrate path. So we are calling it as leakage current here. Okay. So that is how the leakage has taken over in MOSFETs. If it is higher tech nodes, let us suppose 100 nanometer or 180, 90 nanometer, till 45 also we can say it is higher. But less than 45 nanometer if you take, we are still in planar only, we did not enter into FinFET, we are still in planar. So till 45 nanometer it's fine, we have dynamic power, good amount of dynamic power, that's what we want. We want less leakage power and more dynamic power, which is the useful power, right? But if you go into the advanced tech nodes, that means less than 45 nanometer, let us suppose. What is happening? The gate oxide is decreasing, channel is decreasing, because of which leakage is increasing. Why leakage is increasing? Because there is no sufficient amount of channel space for the current to flow. So it is choosing the substrate, which is the leakage current, right? So that is the reason why in advanced nodes, if you see the dynamic power and leakage power percentage, if you see, leakage power is almost near to the dynamic power in advanced nodes, that too in planar. Okay. So what different kinds of leakage currents we have? These are the different, you might have heard these terms in our regular textbooks also we have. So the different leakage currents are subthreshold, gate oxide, all this. So what is subthreshold? Whenever we want, generally if the transistor is off, that means we don't want any current to flow. That's the reason, right? We don't want any current to flow, but still some amount of current is flowing, that is subthreshold leakage current. Coming to gate oxide tunneling, the thin oxide has become thin, right? Now because it is thin, electrons are still coming because of the applied voltage. The electrons are crossing from the oxide, and because of the electron flow, some amount of current is flowing which is not required, that is gate oxide tunneling current. Ultimately we want current to flow only in the channel. That is the main thing that we need to keep in our mind, right? That's what is the exact operation of the transistor, of MOSFET. But here, because of decrease in the channel space, these leakage currents are getting introduced. And junction leakage, if you see, we have source and drain diffusions where, if you see, let us suppose N MOSFET. we have N-type source and N-type drain diffusions, right? And the substrate is P. So at both the sides we have a PN junction diode form, right? Are you able to visualize? So because of those PN junction diodes, the leakage. So if the channel length is decreasing, what is happening? The current is flowing downwards in the substrate. That is what is the leakage current. So that leakage current is junction leakage here. Okay, at the source and drain diffusions, whatever the current that is flowing, that is junction leakage. Why it is called junction? Because a PN junction diode is formed between the source diffusion and substrate, or drain diffusion and substrate, and hence we are calling it as junction leakage. Okay. Gate induced drain leakage. So the name itself tells what this leakage current is. High drain voltage, which is not required. Low gate voltage. So gate is giving little effort. With little voltage also the transistor is getting on, because the oxide is less now. Gate oxide is very less. So with the smaller voltages, the current flow has started, and you are increasing VDS. So the drain voltage is getting increased. So because of that, gate induced drain leakage current gets introduced in the MOSFET. Right? So these are the different leakage currents that we have. So finally, the short channel battlefield is nothing but these are the short channel effects that are there in a single transistor. So one planar MOSFET should handle all these short channel effects. So if you are using a 45 nanometer or 100 to 45 nanometer, then we may not consider the short channel effects, because they don't affect our transistor. But if you go beyond 45 nanometer, then short channel effects comes into picture. Okay, so whatever the points that we discussed, all these are in this transistor now. So the transistor is handling all these short channel effects and leakage currents such that what happens if the channel, we want a chip, the size is increasing, the number of transistors on the chip are increasing, right? What does it mean? If the number of transistors are increasing, then the power consumed by the transistor also increases. That is what is power consumption, and that too we want dynamic power, but here leakage current, dynamic, along with dynamic power we have leakage power also. So if you see, the density of the transistors are increasing, that is what is this loop called power loop. Number of transistors are increasing. Why? We want performance to get increase for any circuit, right? For any chip or circuit. So performance is increasing, that is good. But finally what is happening? Heat increases in the chip. That is because of the heat increase, there will be thermal failures, right? So that is what is this power density loop. So finally we have reached to certain limit. We played with planar MOSFET, we made few adjustments. Okay, we want this till 45 nanometer there was no issue of short channel effects, but we want some other requirement. We have our expectation is increased. Because of the expectation, we need to decrease the channel length to improve the speed. So if we have to decrease the channel length and decrease the gate oxide, short channel effects comes into picture, right? Those effects also our planar MOSFET it has taken. But finally, if you are still not satisfied with that particular speed, if you still want something from the circuit, our expectation is increasing as we go on. So a limit has reached where now the planar MOSFET is out of hands. I mean, it will not work beyond 22 nanometer. So till 22 nanometer, it worked for us. Planar MOSFET served us. But after that, I mean less than 22 nanometer, planar MOSFET will not work as per our expectations, because we cannot compromise for the leakage currents that it is giving, because our requirement, we need to go beyond, because we cannot kill our expectations. So the other thing that we are trying to use is, because the limit has reached, we are entering into FinFET. We are trying to see how the FinFET works, how we can use the other structure of the MOSFET such that at least we can use that structure or that transistor such that it is meeting our expectations, it is fulfilling our expectations. So if you see the FinFET, this is just the introduction where till 45 nanometer our regular planar MOSFET is working fine without short channel effects. Less than 45 nanometer also we worked with planar MOSFET, but it is giving short channel effects, right? Now, so that's what is this. We have seen that there is some issue with the planar MOSFET. Now, because we are not satisfied with the planar MOSFET, now the idea that has come, from where the leakage is happening in the planar MOSFET? From the substrate. Generally the current should flow in the channel, but it's not happening because drain has introduced, drain got entered into the channel. The complete current is flowing in the substrate, we are calling it as leakage current, right? Now, okay, let us think that if there is no option for the current to flow in the substrate, that means we need to restrict the current such that it is not flowing in the substrate, right? So for that they have surrounded the channel with gate, because gate should not lose its control over the channel, right? That's what is the general operation of the MOSFET. If gate loses its control over the channel, then what happens? Leakage current increases, right? But here it is not the case. They have changed the structure itself such that gate is occupied 3 sides. See here, left side, right side and top. All 3 sides gate is occupied such that we can reduce the leakage current. That's what is the intention behind this structure. Okay. And whatever the cyan color is there, that is this one. That magenta color is the gate and the cyan color is the fin of the transistor. We call it as, okay, because this is the fin, we are calling it as FinFET, field effect transistor, and we have the fin and the current flows through that fin, right? Now, so if you see this, if you see the cross-sectional view, that means front view of this diagram. The front view of the diagram is this. Okay. Generally, if you see here, this is the gate. Beneath the gate we have channel, which is fin. Okay. Where is source and drain? Generally, if you take planar MOSFET, we will have source diffusion and drain diffusion, and in between we will have gate. Under the gate, there is a channel and current flows. So here also it is the same, where we have left side source and right side drain. Now, this is the front view of the same figure. So, that we have, so if you say that it is front view, we have source and this is the fin that you are seeing, and at the back of this we have gate. Let us assume like that. Okay. So this FinFET is also called multi-gate because the gate is occupied across 3 sides of the fin. So it is called multi-gate device. So this is the architectural shift. Previously our planar MOSFET is like this, where we have, why it is called planar? Because we have source drain and a gate, right? But if you see the FinFET, the gate is surrounded across the fin 3 sides. So what are the parameters? Okay, if you see, generally you might have seen MOSFET where we will have width, length for that MOSFET, right? If you take planar MOSFET. So what are the parameters that we need to consider for a FinFET? So we will see what parameters we need to consider here. Here also we will have width, but in order to get the width, what terms we need to understand in FinFET? So if you see here, this is just the fin. Our intention here is we want only fin to understand. You know source and drain diffusions, that is common, right? The purpose of source and drain diffusions or drain terminals are, we will source generally will give the electrons and drain will take the electrons. Let us just assume like that. But the control or the current flow is happening because of the gate, and it is happening in the channel, right? So here the fin is doing all this in FinFET. Current is flowing in fin, right? And gate is surrounded on all 3 sides of the fin. Now if you see the fin, it has height and width. If you see the height, you have left side and right side for this fin. So if you see here, this is one height and this is the height, other side of the fin height, right? And this is width. But here we are not considering the width. The reason is, at the bottom we have silicon substrate. Over the silicon substrate we have placed the fin, right? Now, so if we have to discuss about this width of the FinFET, we have 2 sides of the fin, 2 heights of the fin and 1 width. That is the effective width of the FinFET. Okay, so not FinFET, fin. Now, so FinFET, we have started using FinFET from less than 22 nanometer. Till 22 nanometer, our planar MOSFET worked, but with few short channel effect and leakage currents. But so less than 22 nanometer, let us suppose we are using FinFETs. If we want to use the same FinFET for less than 5 nanometer, from 22 to 5 nanometer, we are using FinFETs. Okay, I repeat this. Till 45 nanometer, we are using planar MOSFETs. From 45 to 22 nanometer, also we are using planar MOSFETs, but with short channel effects. Less than 22 nanometer, the planar MOSFET has got breakdown, so we move to FinFET, right? Now we are in FinFET. That means we are in 22 nanometer technology nodes now. So what is happening in 22 nanometer? We have seen that fin where we have 2 heights and 1 width, and it is giving our effective width. But if you want to go beyond, less than 5 nanometer, 22 to 5 nanometer, FinFET is working fine. If you want less than 5 nanometer, what happens? Actually the current flows if it has ample amount of space such that it will flow from source to drain. That's what is happening in regular conduction. Current flow is like this. But the sizes of all the terminals, whether it is gate oxide or channel, whatever you take, the sizes are getting reduced, right? If that is the case, then there is no space for the current to flow, right? So it should choose, the current flow should choose only certain space. So that is why the current is flowing in discrete levels. In this energy levels, the current is flowing. But if you see this case, it has ample amount of space where it is flowing. Of course, leakage is also happening. That is the main reason, because it has more space. Previously, leakage was happening. But here, there is no space, only confined space was there at present. So because of that, the current direction is that focused. Is this point clear? So that whatever the description that I have given, that's what is this. You can just go through it. Coming to the other parameter, because of, let us suppose in the FinFET we have one fin and that one fin is carrying current. But I want current, more current. Okay, more current means speed also increases, right? Let us add more number of fins such that current increases. That's what is happening here. Number of fins are getting added. So if the number of fins are added, then both the fins carries current. That means current is increasing, speed increases. Speed is increasing means delay is decreasing. Yes or no? So if you see, the blue color one is the gate here, right? Because we know that in the FinFET, gate is covering all three sides of the fin. So this is multi-fin architecture. While manufacturing the FinFET, the points that are to be considered are the fin pitch. That means the distance between the fins. Here also if you observe, the gate is surrounding all three sides of the fin for each fin. We have three fins here. For all the three fins, the gate is surrounded across three sides, right? And between the fin to fin, whatever the distance that is there, that is called fin pitch, and the distance that is there between gate to gate, that is gate pitch, right? Now we'll see more on drive strength in the coming slides, but one fin, suppose if we have one fin, that means it is giving some 100 nanoamperes of current. If you have two fins, that means the second fin also carries 100 nano of current, right? That means current is getting added. So third fin also gives 100 nano. So likewise, the current is increasing. That's what is the drive strength. Okay, as you increase the fins, current also increases. That's how the current is flowing in the FinFET.
Can we increase number of fins as we like?
Yes, I'll show that. Because, yeah. No. Yes, we have the option to give the number of fins, but
for a particular
value. Yes.
So what is the maximum limit? Like
It depends on the technology. Yes, it depends on the technology. If you are working on 6 nanometer technology, it is not, generally they give all this in the data book. So if you try to give the more maximum number of fins, let us suppose in 6 nanometer technology, if maximum number of fins we can give are suppose 14. If you try to give 15, then the tool will not accept. So by that you can, because data book,
maximum driving current.
yes. The next parameter that is considered for FinFET is number of fingers. Here the important point that we need to understand is, here finger is nothing but gate only, gate finger. Generally even I got confused when I was working at the starting. So this is not a separate parameter, but it is the gate itself, gate of the FinFET. So if you see here, we have a single transistor. We don't want transistor to be this large. Always we want the transistor to be this small, right? So they'll divide the transistor into some parts. Let us suppose 4 parts. If that is the case, then we will have 4 fingers. That means 4 different gates we will have. That is what is this picture shows. Each gate strip is called 1 finger. Okay. NF4 means, that means we have the single transistor got divided into 4 gate strips. But we can consider the whole structure as single transistor. We will see why this parameter is important, for what purpose they are making NF equal to 4. We can directly use, anyways, the FinFET is used for less than 22 nanometer only, right? Then what is the need to break or divide the single transistor even in 22 nanometer technology? I repeat this point. See, we are using FinFET for 22 nanometer, less than 22 nanometer technologies, right? That means small transistor. Even if we are in small transistor, why we are dividing the transistor gates into pieces? That we will see in the coming slides. Okay, just remember this point. It behaves as a single transistor, but there is a reason behind it why we are breaking it into pieces. The same single transistor we are dividing it. So what is the concept of NF? It is the same. If you see here this structure, if you see, there are 3 pins and 1 finger. That means the same gate we are giving for 3 different pins, right? So in these 3 pins the current is flowing. Yes, the purpose of pin is to have current to flow in the pin, right? So we have 3 conduction paths for this, right? That is what is this. The reason why we split the gate into fingers, or the reason why we split the gate into gate fingers, is for the purpose of layout. Because generally in the industry, the single person will not do from starting to the ending, from circuit design to layout, chip design, till last point. The same person will not do. Circuit designers are different, layout designers are different. Circuit designers, they have to design the circuit such that the circuit is comfortable for the layout designers also to draw the layout. Ultimately, layout is the one which is giving us the area. Yes. So if you give, if the transistor size is, let us suppose we have added number of pins 4, and because we want more current, because the circuit designer's interest is to improve the speed. To improve the speed, what I did, I'll add more number of pins such that my job is done. That is, I'll increase number of pins to 8 such that okay, whatever the speed that is given, what is the spec that is given to me, that is met. So for that I have added number of pins equal to 8. That means if number of pins equal to 4, the size of the transistor is this much, because we have 4 parallel pins. But if I add, as a circuit designer, if I add more number of pins, that means we have double the size of the such that we'll divide the gate fingers such that instead of placing side by side, we'll use this technique where the same gate is used for the all the 4 fins or for all the 8 fins. Okay, so that is, so whatever the fingers that we are dividing, that is for layout purpose. We'll go in detail in the coming slides. So in the part, as part of layout efficiency or improvement in the layout, what's happening? Gate resistance is improved, reduced gate resistance. The transistor is becoming compact. If the layout designer is planning the space on the chip, then he may connect, he'll plan the routing also between terminals to terminals, right? So like that, the routing also gets improved and better matching. What is better matching is, suppose if you have inverter, let's simple example if we take, we have inverter, PMOS and NMOS we want same number of fins, same number of fingers for PMOS and NMOS. It is not that one is given, okay, generally in planar MOSFET, what we do, mobility of for PMOS will give 2 times higher width than NMOS, right? Why? Because hole mobility and electron mobility both are different. So to balance it, we give like that for planar MOSFET. But here also we can do that, but the problem is this mismatch. To have better matching, we give same number of fins for PMOS and NMOS. Same number of fingers for PMOS and NMOS. That is matching. We'll see still in the coming slides. The other parameter that we have is the multiplier. So NF, if you take single gate, we are dividing and the same gate is used for all the fins. Right? Now, multiplier means it is different from NF, that means gate fingers. We are, suppose if you want one transistor, suppose I have a transistor A, I want to use the same fins, same fingers second time also in the other circuit, or second time also I want to use the same A transistor. Then we multiply it. Right? That is the multiplier. I will show in the tool how the multiplier is. That means if you are using M equal to 2, that means it is different transistor, not the single transistor. Of course, we don't see it as the separate transistor. We don't see it as second transistor, transistor A, transistor B. But in the layout, we can notice that they are different transistors. I repeat this. NF means it is single transistor. We don't see any second transistor. But if it is M, if you are changing M for a transistor, we have FinFET. See here, this is just the example where I have just instantiated few transistors, right? So in this transistor, we have fin which is 8 here, and NF I have given as 8, okay? But if you see this N2 transistor, I have given M as 3. Did you notice this? M I have given as 3. See my cursor, here it is. M is given as 3, but in the schematic you are seeing it as a single transistor only. We are not seeing it as a different transistor, 2 transistors we have or 3 transistors we have. Although you increase NF, M, we see it as a single transistor. But if you see the layout, This is instance N2. If you see the layout for m equal to 3, N2 is this. See left side, my multiplier is 3, right? Because it is 3, you are seeing 3 different instances. Yes or no? Here you can see. Here you can see 3 different instances, which is M1, M2, M3. Okay. And the same N2, if you see the layout here, okay, it is showing instances M1, M2, M3, but right side if you see there, this is, okay, let me select here. Here we have M1, M2, that means we are seeing it as a different transistor in the layout, but not in the schematic. Okay. Similarly, if here NF is 2, right? For instance N1, NF I have given, fingers I have given as 2. In the layout, we don't see it as different transistor. See, this is N1. Okay. How do you identify that we have NF equal to 2 in the layout? If it is for n equal to 3, we have seen 3 different instances, right? For n equal to 3, we have seen 3 different instances. But here I have given NF equal to 2. But how do you notice that? That is, how we notice is whatever the small gray horizontal lines that we have, they are fins here. In the tool, these are fins. Okay. Now, fins and NF is gate finger only. Those fins should cross 2 gate fingers. So, these are the gates and these gates are crossing. These gates are crossing these fins. I mean these fins are 2. See, all these are fins. Okay. These fins in this, for this transistor, these fins are crossing these 2 gates. Okay. So that way we should identify that it is a single transistor and NF equal to 2. And if you see this one, N5, in the schematic I have given NF equal to 8. That means gate fingers I have given as 8, right? And here, how many fins those gates are crossing? How many fingers we have? These are the gates fingers, 3, 4, 5, 6, 7, 8, right? Leave the last and either ends of the red colors, you leave it. Those are source and drains. But whatever the middle ones we have, those are the gates which are NFs. Okay. So, those number of gates will cross the given number of fins. So, here how many fins I have given for N5? I have given number of fins as 8. I am showing you the schematic now. Fingers are 8 and fins also 8. That means we have 8 gates crossing 8 fingers. So, if you see here, we have those fins. I said these are fins, right? Count 3, 4, 5, 6, 7, 8. 8 fins we have, and these are the fingers that are crossing these 8 fins. That's how we will denote or give in the tool. Okay? So now we have noticed that Multiplier means different number of transistors. Of course, we don't notice that in the schematic again. We will notice that only in the layout, right? All these parameters, generally if you see only the schematic, we don't notice that okay, this is the parameter which is important. Why we are discussing all this is, the important reason is, it is not that only you design something according to your requirement as a circuit designer and throw your circuit to the layout. It is not like that. You have to collaboratively work such that our design is this. Okay. So, what is, from the layout designer point of view, what is his interest? NF or M? NF or M? It depends, but generally we don't prefer M because it increases area. From layout point of view, area should be less. So, it's not that the layout designer will always rejects M. It's not like that, because he should give respect to circuit designer's views also, because finally the specs should melt. So this is M. So what this image indicates is, if M equal to 1, we have only one transistor, but if M equal to 4, we will have different number of transistors, right? But in the schematic it is shown as single transistor only. How? Gates, drains and sources are all connected internally. Okay, that's what are these connections.
Ma'am, what parameter does N or M which signifies? What kind of parameters? Like more current due to N or more?
No, all these comes under width only. Okay. See, finally if you remember the current equation, it is W by L mu n C ox W by L VGS minus VGH whole square for saturation region, right? W and L are the important parameters for us. W effective, NF, M, all these three, NFIN, the NF, M, all these are for width.
So L is fixed.
L is fixed for a particular technology, but in that particular technology also we can vary according to our convenience. There is some limit. Let us suppose if it is 22 nanometer technology, the maximum value is 22. The minimum value is 22, but less than that we cannot go. Because in some analog devices, in some analog circuits, that circuit may not operate according to our requirement, the spec may not be such that we may have to increase the length. In some cases, it does not happen, but generally, just for an example I am telling, if we have to increase the length, then you can increase, but not more, you cannot increase too much, but if it is 22 nanometer technology, let us suppose we are doing 30 nanometer, then it is fine. So, you can improve or increase the length, it is not fixed for a particular technology, but we cannot go beyond the value that is given in the data book. So, here if you see, this is them, still we are in width only, all these parameter comes under width. Okay, NF versus M. Although both parameters NF and M comes under width, also we have seen the difference. NF means single transistor, M is different number of transistors, that we can notice only in the layout. Now see the advantages. Suppose if you want NF, in the circuit also, while designing the circuit, you will increase, the reason why we increase W is to increase the current. We want increased current or high current because to increase the speed. Final goal is that, right? W by L, right? I is directly proportional to W. If you increase W, then only I increases. Yes or no? So, Why in the process of increasing that W, we are increasing NF. Okay. When you should increase NF, when you should increase M. That's what is the discussion now. Okay. Now, if you see NF, if you, okay, NF, for example, if NF equal to 4, that means we have 4 gate fingers. That is fine. But what is the advantage? Is diffusion sharing. That means if diffusion is nothing but source and drain diffusions, right? So source, suppose if you have one fin here, somewhere here we have seen NF, right? If you see here, we have, this is the gate, right? Single gate, and we have fins. So let us suppose we have, you are seeing my cursor, right? You have source here, and next side of the fin you have drain. That same drain you can share it with the second finger also, second fin also. That is diffusion sharing. And here if you have drain, next side if you have source, the same source you can use for the third fin also, right? That is diffusion sharing. And because of this diffusion sharing, the capacitance that is produced because of this diffusions, you might have seen the junction capacitances, right? That capacitance also decreases. That is also one of the advantage with NF, and because of which area decreases. And routing also, we no need to give more, we no need to break our head to give how to connect between the sources, between the drains, all that. So these are the advantages that we have if you break or if you split NF into, if you break it or if you divide the fingers. Okay. So if you want these disadvantages, if you want these advantages in the circuit, then we go for increase in the NF, right? And from layout perspective also, it is more efficient. So when do designers prefer each? When we want NF and when we want M to increase. So NF we want when we want smaller area and layout to be compact. If that is the case, we use NF. And if we want M, then when do we use or when do we increase M is when you want same device, same type of transistor, if you want to use it multiple times, then we use M. So generally that they are used in analog circuits. And if you want, suppose for that particular M, for that particular transistor, if they have created the layout, the same layout they can reuse, the layout engineers, they can reuse. So that is also one of the advantage. Although the circuit designer, he has created M equal to 4 or M equal to 2, then it is sometimes advantageous to layout designers also, because he will reuse the same layout. That means effort is reduced for the layout engineer. Coming to the other parameter, which is stack. Okay. Now the W part of the FinFET is done. Now we came to the L part. Okay. As of now, we are discussing the parameters, FinFET parameters. In the FinFET parameters, our interest is W and length, width and length. Fins, fingers, multipliers, all these covers the width of the transistor, width of the FinFET. Stack is the length of the FinFET, which stack is the point where it is the length. Okay. So if you increase the stack, there is one, so if you see in the tool, there is, okay, there are stack devices. There are stack devices. So if you see, here we have devices library where we have only single stack devices here. But we have device stack where we have stack devices. Okay, there is different library where we will have different stacks, the same devices we'll have, but we can increase the stack. Okay, so you have to instantiate the stack devices from devices stack library, and there how many number of stacks you want, you can give accordingly. But what happens if L is increased? I decreases, because I is inversely proportional to L, so current decreases. So according to the requirement, we will play with these parameters. So this is the stack. So what exactly, how the transistor looks like is, stack is nothing but the transistors are connected like this in series, and the current should flow in both the transistors. Then only the function of the transistor happens, otherwise the transistor we can say it as off. Okay. And next, so if you see in the fabrication of FinFET, it is not that we are constructing or fabricating the FinFET upward, it is outward. Outward means, see the fins here, fins are not placed one top of one fin over the other, it is not like that. It is first fin, second fin, third fin, horizontally we are placing, it is not vertically. Okay, remember this word, we are not placing fins vertically, they are placed horizontally. Okay, generally it is just the assumption that there is no place this way, that is the reason we are increasing or improving the transistor by increasing by fabricating the transistor like this, one top of the other. It is not like that. Hope this point is clear, right? But there is a technology where vertical stack is also happening, that we will see in the coming slides. So what all the design constraints, 5 minutes we will see a few points and then we will go for break. There is a problem, of course we have seen what are the parameters that we have in FinFET, but there are some issues also with FinFET. So what are the issues that we have? We are calling them as design constraints, that is no arbitrary sizing. Suppose if you take planar MOSFETs, there whatever the width you want, you can give to that MOSFET for a particular technology. Let us suppose if it is 180 nanometer technology, then you can give 20 micro or 30 micro width, any width you can give. But here in FinFET we cannot give the width like this, because it depends on number of fins, right? Fins cannot be any value. We cannot give 2.5 fins, 3.5 fins like that. Either it should be 2 or it should be 3. So that is no arbitrary sizing. Okay, matching constraints. Okay, let us see this. So design constraint is the one which I discussed now. The value of the fin should be an integer where you cannot give 2.5, either it should be 2 or it should be 3. If you want more power or its performance should be more or good, if the performance of the circuit should be good, then we'll prefer to give more number of fins. That means if you want 2.5, then we prefer to choose 3 fins. You notice the point here, our requirement is 2.5, but we don't have the option to select or to give 2.5. That is the reason we go for 3 fins. Because if you choose, generally we choose one high, greater than 2.5. The reason is we want better performance. Better performance in the form of current. Good drive strength we want. So we choose higher fin. Coming to the constraint, matching constraints, suppose here also the same point. Generally, if you have inverter, PMOS and NMOS should have same number of fins. It is not that PMOS have 5 fins and NMOS has 2 fins. That will not match. It will not give equal rise and fall times. We want the period should be same. Okay, to have equal rise and fall times, we prefer to give same fins for both PMOS and NMOS fins. So fin grid restrictions, if you see, we have seen the layout, right? Just now we have seen the layout where what you can observe here is the fins are already placed. We have already fins here, right? Whatever the grey lines we are seeing, they are fins. So the fins are already placed. How you use those fins to form a transistor is our interest or our choice. Okay, you can choose any number of fins. Suppose I want 10 fins equal to 8. So I just give the number and fins equal to 8 such that my transistor is choosing those number of fins in this. Yes or no? That's what is happening here, right? See, I said these are the fins, right? These fins are already there. How you are using these fins, that is designer's choice. How designer will choose that he wants fin equal to 8? Because the spec should meet. His interest is to get 100 nano of current. If he gives fin equal to 8, then only if he is meeting the spec. If the circuit is meeting the spec, then you give fin equal to 8. That means you are using that fin such that the transistor is formed. Okay. That means if you see the example that is given here are, if you go for any parking, you will have the parking places. You will just go there and park your car, right? Parking the car is your choice. Where to park is your choice. Yes or no? But, and also space should be available. That is second point. But you will choose the number of fins according to the designer's choice only. Right? Is this point clear?
But it has to be at the W by L pitch.
Yes. We will choose according to, so the W by L, the main requirement why we are choosing fins is to meet the current value. So let us suppose if we want 100 nano of current, that is the given spec to us. So if we want to meet that, if we want to get that 100 nano, we will try increasing the fins, and we will see that if you give 8 number of fins, then we are getting some 110 nano of current. Then we can fix that, okay, for this circuit fin equal to 8, for this transistor fin equal to 8 at this place, then the current requirement is met. So we need to choose according to that.
And one more thing, if W by L equal to 1 and greater than 1 and less than 1, what will be the effect of circuit topology with respect to current and speeds?
So generally
And
W
which is
by L,
favorable?
okay, W by L individually we don't want. Finally, W by L can be any value. That is not the problem. The problem here is if W is increasing, current increases, and if you increase length, current decreases. So with that increase in length and with the increase in W is the spec meeting. W by L can be anything, any value, whether it is 1 micro or 2 micro, it is fine now. But the problem is If the spec is meeting by increasing W, it is fine. Generally, we don't prefer to increase length because that varies the channel length. So we don't prefer to increase stack or length. Worst cases means it is not that. Yes, the first preference is for W, that means fin, NF, M, and next preference if the spec is not meeting, if you are not satisfied with the operation of the circuit, then we will go for length. If we have the option to meet the spec, let us suppose if we have option that if you increase length, then the circuit is meeting the spec, then we will go for increasing length also.
In general, what will be its value, whether it is greater than 1 or less than 1?
W by L, it is not, it should be less than 1 generally, but we cannot say that it should be greater than 1 or less than 1, because sometimes it happens. Okay, because we are talking in nanos, it should be less than 1 only, because all are smaller tech nodes where we have nano technology only. So it should be less than 1, W by L.
And is it necessary to maintain same W/L ratio of all the transistors in one?
No, it is not possible. It is not possible because if you try to keep W by L for all the transistors like that, definitely our spec is not going to meet, because ultimately whatever the spec that is given from our customer, so those specs we should try to meet. So it is not possible that we can have same W by Ls for all the transistors. So final conclusion for this is, according to the requirement, designer's choice, we will choose the number of fins. Okay, so if you want, you cannot take any fin. Randomly you cannot take any fin number.
Suppose in one transistor we have selected some pins. Does it affect other transistors, like when we cascade or join with other?
No.
Will it affect on other properties?
Properties in the sense, suppose you are talking about a single transistor.
Yeah, everything is fine.
Okay.
Pins and all those. So if we like connect transistors in a circuit with other transistors, does this effect will be on other transistors? Like
No.
this, according to this pin, the current will be there. So other transistor may affect the
Okay.
flowing of current.
Okay, let me see this. Suppose you have one circuit where we have some 4 transistors, let us suppose. And that circuit is not meeting the spec. If the circuit is not meeting the spec, first we will identify in this circuit which of these 4 transistors are not, which of these 4 transistors are culprit. Out of 4, which transistor is the culprit such that my spec is not meeting. First we will identify that. So based on that, you will change the parameters of that particular transistor. It can be, it is not that if you change this transistor, the other transistor changes. It happens because in analog, one transistor affects the other transistor also. That happens. But you need to manage, or this pin will not affect the other pin. Other transistors current. Sometimes it happens, but you can vary accordingly. If you are, suppose for transistor A, if you are giving fin equal to 8, for transistor B, because you have given fin equal to 8 for transistor A, if the current flow is changing in transistor B, then you can vary transistor B also, transistor B's pin also, such that the overall circuit is meeting the given spec. Because in analog it happens, if you change one transistor, then the other transistor also get enter into some other region. Our ultimate goal is to have it in saturation, but it will not happen. So while identifying which transistor is not in saturation, by doing you will understand, okay, if you change this transistor, the other transistor also enters into linear region. That kind of analysis you will get it. So accordingly you will adjust the fins or fingers or whatever the parameter you want.
So
Okay, so this completes half part of today's topic. Next is, so till now we have seen why we are moving from planar to FinFETs. So in the FinFET we have seen what are the parameters that we have, width parameters and length parameters, and then the device part is completed. Now we go for circuit part. Okay, this is not that boring and you will have many points that So how those devices are used in circuits, that we'll see in the coming topics. So the next one is, actually I have divided the session into 6 sections. Okay, the first section was, if you see the outline, there are six sections where we have introduction and motivation, where we have seen the limitations of MOS, next fundamentals of FinFET, and then parameters of FinFET. Now we are seeing how the FinFET transistors are used in the circuits. It is like same regular transistors. So in the first half, we have discussed that from 100 nanometer, so okay, till 22 nanometer, we have used planar MOS, right? From 22 nanometer onwards, less than 22 nanometers, we are using FinFETs, right? Now, is there any breakpoint for this 22 nanometer, or why we have moved to the FinFET is because these are the disadvantages that we have seen, short channel effects and leakage currents. Because of these disadvantages, we move to FinFET, right? So the solution is the FinFET. Now coming to the circuit performance, how the circuit performance comes into picture. Okay, we have seen the parameters of the transistor, but how do we decide the performance of the circuit is from the drive strength. We have seen this word in the first half of the session, where drive strength is nothing but the current that is flowing through the fins. That is what is the drive strength. So because of this drive strength, if you have inverter, generally I have to discuss even inverter here in this topic, because the basic circuit that we discuss in any VLSI session or VLSI is the inverter. We start from inverter. If it is digital, CMOS inverter, PMOS, NMOS. If it is analog, then common source amplifier is the inverter that is generally we discuss. But whether it is FinFET technology or normal planar MOSFET, the circuit does not change. The same PMOS we will have, same NMOS we will have if you take digital inverter. The same different kinds of CMOS common source amplifiers will have. So there is no point to discuss here, because you will find those topics in textbook also. But what are the performance metrics that we need to consider if you have that circuit? Whether it is analog circuit or digital circuit, is one of such parameter is drive strength. Okay, so how we need good drive strength? Why we need good drive strength? Because there will be improvement in the circuit. Finally, we want good circuit which meets the spec, right? So in order to increase the drive strength, what we need to do is will increase the number of fins. That's what we have seen in the last session, in the previous first half. So if you have good drive strength or higher drive strength, will have higher current. That means charging, discharging of the transistor happens in a faster way, like that speed increases, right? Finally, that's how the spec is made or our goal is reached. So coming to the same drive strength, how it is in planar and in FinFET. So in planar, it is directly proportional to the width, the drive strength, whereas in FinFET, it depends on the number of fins. Okay. In FinFET, it depends on the number of fins. Why number of fins? We already discussed this. As we go on increase the number of fins, the current flow in each fin increases. Let us suppose if you have one fin in the transistor, it is giving 100 nanoamperes of current. If you increase the fin from 1 to 2, it gives 200 nano. And if you increase to 5 nano, it gives 500 nanoamperes of current, right? So that way, the current is increasing ultimately, which is nothing but speed is increasing. The other performance metric, circuit performance metric is the delay, where if you see the relation here, delay is inversely proportional to the current, right? So if you increase the current, of course we are increasing the fins such that current is increasing. What is happening if current increases? The speed is increasing. That means delay is decreasing, right? So the other performance metric is delay, and this is how the reaction, chain reaction. If you increase the number of fins, drive strength increases and then speed increases. Okay. So if the speed is increasing, that means you will have some penalty, right? If the speed is increasing, that means there should be some penalty, that is in terms of power. Okay, if you increase the number of fins, what happens? Of course, speed increases, but power also increases with that current, right? So that is the trade-off that we have between the delay and power. Now, if you increase the number of fins, that means the capacitance also increases, because across each fin you will have source and drain regions. That means the capacitance increases. If the capacitance increases, dynamic power also increases according to the equation that is here. Okay, so that is the same that we discussed. So there is trade-off between power, performance and area if you increase the drive strength. So then how do you choose what you want? Is again based on the meeting the spec. You need to balance for this particular circuit, what is the important requirement? Is it power or delay? If for a particular circuit A, if speed is important, increase the number of fins such that the chain reaction applies and then speed increases. But for circuit B, if power is an important point, then you don't increase the number of fins because the power increases. Instead, you try to decrease or see what parameter you can change such that power is decreasing for the circuit B. Because if you take a large chip, we will have not only in the chip we will have different circuits, circuit A, B, C. Circuit A's requirement is speed, circuit B's requirement is power. So this is designed separately and B circuit is designed separately, where these two circuits are used by the whole complete circuit. Likewise, the full requirement is fulfilled. What are the real industry constraints? Are fin alignment issues, layout restrictions and matching requirements. So these points are already covered, but we'll see. Fin alignment issues are nothing but, as we discussed, fin value should be an integer. It cannot be 2.5 or 3.5. It should be a single number. Suppose if you want 350 nanometer of current, then you need to choose either 3 fins or 4 fins. It cannot be 3.5 fins. So that is fin alignment issues, right? So that is what is the example that is given here. If you want 350 nanometer, 350 nanoamperes of current, choose 4 fins such that you will have more 50 nanoamperes of current higher, right? Such that whatever the spec that is given, that is met. So this is fin quantization. This issue is fin quantization or fin alignment issue. And coming to the layout restrictions. Okay, we have designed the circuit and we have given the circuit with the layout team. So layout team will start designing the layout or drawing the layout for our circuit. Then they will see the layout rules that are given in the data book. What are the layout rules? How much is the fin pitch, gate pitch? Fin pitch is fin to fin distance Gate pitch is gate to gate distance in a transistor. So all these rules they will check. You know, hope you know this. For any technology, whether it is planar, FinFET or advanced, that is gate all around technology. For all the technologies, we will have layout rules that are already given in the data book. Those layout rules should be followed by the layout engineers. Okay, in the process of following the layout rules, the rules that are to be taken care are minimum spacing between fin pitch, gate pitch, and restrictions on diffusion sharing. Diffusion sharing is source and drain regions. How we have to share. If you take NF, we discussed while seeing NF concept, where we will share, I mean, the source region is shared by two gates or two fins. The drain region is shared by two fins. That is diffusion sharing. So those restrictions, if any rules are given for those diffusion sharing, that should be given, that should be taken care while drawing the layout. And also metal routing. That means while giving the wiring between terminals to terminals, what are the restrictions that are given in the layout rules? Those rules also should be followed. So those are the restrictions that we have in the FinFET. Of course, this will be there in any technology, whether it is planar or FinFET. But the point here is why we are discussing these points is because the parameters that we need to consider here are more. As the technology is improving, the FinFET technology is better than planar. As the technology is improving, the number of parameters are increasing. So we need to consider more rules while drawing the layout. If we choose this, we better choose higher only, because with the 50 nanometers change, there will be no much huge difference in the spec. That is, yeah, that's what I'm telling. With that small 50 nanometers change, so it's again it depends on what kind of circuit you are designing. If A circuit requires less power, then you will choose 300 nanometer. If B circuit requires high speed, then you take 400 nanometer. It depends on what circuit required, what specification. No, we cannot replace. But resistor we cannot place now. Form, yes. No, there is no solution, but it again depends on the circuit performance only, circuit requirement only. As I said, for power, if this 50 nano is also playing major role in the circuit, then you will go for 300 nanometer. So with this layout restrictions, if you keep all these rules in mind and if you draw the layout, what is the physical penalty that we have is the congested routing and poor placement. We need to violate manufacturing rules. Resistance and capacitance also increases, and ultimately delay increases. So coming to the next industry constraint, that is matching requirements. As we discussed, number of fins should be same for PMOS and NMOS. If you have two transistors, then two transistors should have same number of fins such that the mismatch will not happen between two. So manufacturing violations can be these threshold voltage drift, current drift, and offset voltages. So while drawing the layout, if you observe, You have two transistors, PMOS and NMOS. Let us take it as A and B. So instead of place each transistor should have same environment. Transistor A and transistor B should have same environment such that the operation of the transistor does not change, such that whatever the requirement that is required, that is fulfilled. If you see, the process variations does not see whatever the process variation effects that we have, those process variations also affect the transistor A and transistor B in the same way. Okay, so that is the point here. If you place the transistors like this gives better matching because all the transistors are in a closed circle. I mean, they are at single point. Here, the transistor is spread like this, right? Where the process variations, that is threshold voltage, that is one of the process variation. So those variations are different for this transistor, for this transistor. Whereas if you place side by side like this, then what happens? The process variation affect A and B in the same way, such that there is no mismatch between the transistors. That is what is this layout technique is for matching. The other layout technique for matching is interdigitation, where suppose we have different fingers. We have seen the example of different fingers where fingers are example which we have taken is NF equal to 4, where instead of placing all transistors at one place, all type of transistors A at one space at one side and transistors B at one other side, instead of placing like that, if you place alternately with A, B in this way, then all these transistors will have the same kind of process variations, and those all process variations are average, such that you will have same environment for the complete circuit or for that particular circuit on the chip. So from device sizing to system performance, so if you see, we need transistor sizing. From once the transistor is sized, then we will have standard cells and then library creation. After that, okay, let me show you. This is the standard cell library. If you observe here, we have SC underscore LVT. This is standard cell library. SC is standard cell, where we have these many cells. Why we have a separate library for all these for the standard cell is, the standard cells are nothing but inverters, NAND, NORs, flip-flops, the basic digital circuits where you use the circuits frequently. In any circuit, if you take any big chip, these are the standard cells generally we use frequently. So we will create a separate library for such kind of standard cell, and we use them we'll use them whenever we want on the chip, right? Now, so if you see this slide, this is for that standard cell library also, we will have the library. So we design the standard cells, that means inverter, NAND, NOR, flip-flops, all that. Once that library is created, we will characterize. That means characterization is nothing but we will find the propagation delay, rise time, fall time, all those measurements we do. Once those measurements are done, then we'll go for timing closure. So we'll see transistor sizing. We understood how the transistor sizing is done. transistor sizing is done by increasing the number of fins, and then we'll design the standard cells, and then using different standard cells a library is created like the way which I shown, and then we find the measurements. We'll run the simulations and find the measurements. Those measurements are nothing but delay, rise time, fall time, setup and hold times, all those are the measurements. And then timing closure. Timing closure is nothing but, suppose the given clock period is 1 nano, but if the circuit is taking more time and it is completing its simulation in 1.2 nanoseconds, then that means it is a timing failure. Okay. So, in order to avoid that timing failures, what we do is, we'll increase, these are the techniques that we do to improve the timing. Either we replace inverter cross one, either we increase the drive strength. What is happening here? If you see the failing path, here, the drive strength, if you have one drive strength, then the delay is this much. That means actual time clock period is 1 nano, but it is taking more time. That means it is a failure. Now we have increased the drive strength from 1 to 4, and here also we have increased the drive strength from 2 cross 1 to 2 cross 4. As we increase the drive strength, it is taking less time to complete the time. That is, speed is increasing, right? So this is the technique that we have used. This is just the example, and these are the timing optimization techniques that we have, that we follow generally in industry. So this is, so from transistor sizing to timing closure, how the steps, what are the steps that we have. So transistor sizing is nothing but increasing the number of pins, that is device level, standard cells, that means inverter, NOR, gate, NOR, flip-flops, that using all those standard cells will create a library, do measurements, then do measurements means run simulations such that you will get propagation delay, all those measurements, and then see whether the timing is met or not. Now coming to the advanced nodes, that is gate all around. So till 22 nanometer to less than 3 nanometer, 22 nanometer through to 3 nanometer, the transistor FinFET technology is working fine. But less than 3 nanometer, FinFET is, but for less than 3 nanometer technology, FinFET is also not working fine, because of which we are going for the advanced node, that is gate all around technology. So in gate all around, so what is the difference? In planar MOSFET, we have seen that there is leakage from the in the substrate. Whereas, because in order to avoid that disadvantage, or in order to avoid the limitations that are coming from planar MOSFET, we went to FinFET. What happened in the FinFET? The gate is surrounded all the 3 sides, but from where the leakage is happening? From the bottom side. Because there is no gate that is protecting the FinFET, such that there is leakage at the bottom. There is no gate in the bottom, as we see the FinFET technology. Now, so from 22 to 5 nanometer, FinFET is also working fine. Whatever the leakage that FinFET is giving, that is also acceptable. But what happened if it is less than 5 nanometer technology? That means FinFET is not working properly. That means it is not meeting our requirement. Whatever the spec that we have given, it is not meeting. So we have moved from FinFET to gate all around technology. So what is happening in gate all around technology? Even the fourth side also covered with gate. If you see the left, this one is the FinFET, where we have 3 sides covered. The fin is covered the 3 sides, but in GAA it has all the 4 sides gate. Okay, that means leakage is still reduced. So how the evolution is happening here? If you see the planar, you have this, the leakage is happening in the substrate, whereas in FinFET the bottom is the place where leakage is happening. But in GAA, that is the third place, if you see this sheet, we have discussed in the first half that we have, this is the vertical fin, right? But here, the fins, we will not call them as fins, but we will call them as sheets, nano sheets or nano wires. They are placed horizontally. Each nano sheet is covered completely with a gate. That means all the four sides. If you take one nano sheet, or the single nano sheet is covered four sides with the gate, such that there is no leakage. Okay. So this is how, this is the front view. Whatever the below structures you are seeing, that is the front view of the three technologies. So FinFET is vertically the fins are raised, whereas in GAA the nano sheets are horizontally placed. Okay. The same, each and every sheet is covered with all the four sides are covered with gates such that the leakage is reduced. So if you see the conduction paths, for more current to have in FinFET, what we are doing? We are increasing the number of fins. Here, we will increase the number of sheets. The nano sheets, the horizontal sheets will increase such that the current is increased. So, however, we have three conducting paths. Here in the example, here we have FinFET where we have three parallel conducting paths for current. In the nano sheet, we have, in the GAA, we have three nano sheets such that we will have three parallel conduction paths here, but the only difference is vertical and horizontal. If you see here, this is the drive strength. We have seen what the drive strength is. Ultimately, we want more drive strength such that the performance of the circuit improves. That's what we have seen, right? So how the drive strength is improved in FinFET and GAA is, see here, these are the gate fingers, the blue ones. These are the gate fingers and these are fins. We have seen in the tool that there are fins which are covering the gates. So, 2 fingers and 3 fins which is giving 6 fins totally, right? So, if you want same 6 fins in the GA technology, we have that kind of structure. 3 nanosheets will give with same 2 fingers. So, what we want to understand here, FinFET and GA both are same. But if you are going for lower tech nodes, less than 3 nanometer tech nodes, then we'll choose GA technology. Why? Because there is less leakage comparatively. That is the main reason why we are going to this GA technology. But the operation and the parameters all are same. So, however, we have discussed different parameters in GA, in FinFET. Those all parameters apply same here for GA as well. Okay. So, how the current is flowing in FinFET and GA? Their fins we are increasing. So, W by L there in FinFET, W is nothing but number of pins, fingers and multiplier, right? Here also same. Instead of pins, the only difference is nanosheets, right? So if you see the total current, the current that is flowing from fin 1, 2, 3, all that is added to get the total current in FinFET. Whereas in gate all around, we have each sheet, each nanosheet and width of nanosheet. That is also considered to get the total current for GA. So this is the comparative summary between FinFET and GAA, where both are almost same. The only difference is the leakage. We want more less leakage. Whatever the leakage that is given by FinFET, it is less compared to planar it is less, but still for lesser tech nodes, for less for less than 3 nanometer tech nodes, this FinFET is not fulfilling our requirement. For that reason we are moving to GAA, and that is fulfilled here where the leakage is less, right? So we have seen the device parameters and how those devices are used in the circuit in the form of standard cells. Now we know we have some flow in the circuit. We have some flow. How we do the simulations, whether it is schematic simulations or layout simulations. Now, how AI is involved? Is it possible to use AI in this flow? That is what we will see just 5 minutes. So if you see from 100 from till 22 nanometer, it is planar MOSFET. From 22 to 5 nanometer, it is FinFET. From 5 nanometer or less than 3 nanometer, it is GAA, gate all around, right? What did you notice between planar and FinFET? Number of variables are increasing. Yes or no? For planar, we have WL. Those are the two major important parameters that we are taken into consideration for planar. But for FinFET, it is not only W means it is not only the single variable W. We are taking NF, fills, multiplier. These 3 points, these 3 parameters we are taking, whereas for L, we are taking length and stack, right? That means the number of variables are increasing as the technology is decreasing. That's what is this slide shows. So, if the number of variables are increasing, then while drawing the layout engineer should consider all these rules which are related to these parameters. Yes or no? Right? So, what is the conventional design flow is, it is not that the customer will give the spec and the designer will draw the or design the circuit and layout engineer will give the layout for the circuit. It is not that. Before that, some 3-4 months time, first let us suppose we have one circuit, one inverter we have in 180 nanometer technology, but the customer's requirement is, it is not 180 nanometer, they want a circuit in 45 nanometer technology. Same inverter they want in 45 nanometer. Now, the industry will not design again from scratch. Then convert 180 nanometer inverter to 45 nanometer inverter using some rules. And that we call it as technology migration. That means we are converting one circuit from 180 nanometer to 45 nanometer technology. So that means we are not designing the inverter from scratch. We don't instantiate PMOS, NMOS, and then new winding, all that we don't do. Right? We'll just convert from 180 to 45 and then start running the simulations whether it is working fine or not. In the process of C, because it's fun, we have 180 nanometer circuit and we are moving to 45 nanometer circuit by migrating from or by converting 180 to 45 nanometer. We will have the circuit, but we don't know whether the performance is correct or not. Right? The tool is doing that conversion from 180 to 45. In the process of conversion from 180 to 45, how the tool knows what it has to do, how it will perform, that is by the conversion engineer will create the rules. If you see, this is, I'm just blindly showing the rules that are created. This is the source technology. That means 180 nanometer technology. And this is the target technology where we have 45 nanometer. So, let us suppose if the circuit has this device, then this particular device will have this parameters in the target. That means in the 45 nanometer technology. Okay. This used to be done manually by running simulations. How a target, how 180 nanometer device is giving the current. We'll try to match the same current with 45 nanometer device current. If the both devices, 180 nanometer and 45 nanometer devices currents are meeting, then okay, these are the parameters we can fix for 45 nanometer device. That's how we used to create rules manually. But now all manual works where manual efforts are more, those manual efforts are replaced. They are trying to replace those manual efforts with some automation. But still it is under exploration. The reason is we don't know, we cannot stop completely the completely manual work and completely depend on automation tasks. The reason is we don't know whether the automated circuit gives the correct results or not. Okay, so still it is under exploration, but there is, some teams are working such that whatever the manual efforts are, wherever the manual efforts are more, they are trying to automate it such that the task can be completed fast, because it takes 3 months, but they want the task to be completed, the company want the task to be completed in 1 month. So then they have to do it automatically only, right? So some automation rules are created and not sure whether it works properly or not, right? So this is the conventional design flow that generally any industry, any company use. Migration, that means from one technology to the other technology, they'll convert and then run the simulations. We'll get the circuit, right? Once we convert, each company will have their own software for converting from one technology to the other. We don't have any tool. We use script. There is one script, and the script is used in the same. We have in the guidance we have. In the same way, Synopsys custom compiler is there. In the custom compiler, they use that script. They have given that script in the custom compiler. We use that script to convert from one technology to the other technology. But before using that script, we need to design the rules. Because, but it takes, only for conversion, it takes 1 year, more than 1 year. But the whole project to be completed in 6 months. That is the target. So that takes more time, but they'll not give that much time. So for that reason, the script is developed and they're converting from one technology to the other technology. It takes, no, it is not very long. They use sticky script. It takes 2 months. Script is already there. So for each technology migration, they'll not use script. So from, suppose if they are converting from TSMC to Samsung, TSMC will have some parameters to be considered for a device, and for Samsung, some other parameters we need to consider. So how to match these parameters in TSMC and the parameters that are available in Samsung? How these parameters have to be matched? First they'll check, and then they'll directly implement the same code for this migration.
Is it not possible to replace the transistors from one to another? If we get all circuit is already designed, I think 180 nanometer. Suppose we take the transistors and change to replace by 45, doesn't it work?
No. Now, take version only. You have designed inverter in 180 nanometer. With the same 180 nanometer, you will be able to replace that devices in 45. You have to open the tool again in 45, then you will be able to. Also, you cannot copy one transistor from one techno to the other techno. If you open two version source, you cannot copy this 180 nanometer inverter is 45 nanometer inverter.
Like when we try to copy and paste from IT to IT, like all circuits were copied, but the transistor was
Yeah.
so in that case, we just use the other technology.
But again, if you have inverter, then it's fine. You can replace, because you have only 2 transistors, you will replace PMOS and NMOS. But if you have some 100 transistors, again, that is a manual work. You need to replace all 100 transistors manually, which is a big manual work. So that's the main reason actually. See, here I am giving the example because I am taking the example as inverter because we have, that is the easy one which we can analyze. That's the reason. Okay. Oh, okay, sir. Last.
Any questions are there? We just don't fair. We can take
So, final conclusion is in circuits with AI, or what is the role of AI in VLSI? In each and every flow. So, it is not that we will have final circuit directly, right? If you take any techno, we will not directly get final circuit. We will have some flow to follow. So, in all these steps, they are trying to do research and trying to get where all the possibilities that we can involve automation. So that is still exploration. So if we come up with some kind of good automated flow, then it's good. So that's what is happening right now in our company. It's not that the flow is fixed for AI for all the steps. It is not like that, but they are trying to do whatever they can do. So finally, we have seen from device to circuits, and after that, how AI can be used. This AI part still we need to discuss, because there are many steps that we can use AI, but we can have it in the other separate session. Maybe I'll have more data by that time. Okay, thank you.
Thank you very much, ma'am, for an excellent and highly informative session. Your insights into FinFET technology, SOC design methodologies, and the role of AI in next generation chip design have been truly enlightening. We sincerely appreciate your valuable time and knowledge you have shared with all of us. As a token of our gratitude and appreciation, I request our Honorable Principal Sir, Professor JVR Ravindra Sir, and Convener of ATAL FDP 2026, Dr. J. Krishna Chaitanya Sir, and Coordinator of ATAL FDP 2026, Professor Rajendra Sir, to kindly felicitate our esteemed resource person, Dr. Lavanya ma'am.
So today's guest, Dr. Lavanya ma'am, has actually worked in this college as faculty. Then she moved to the industry for Synopsys. She has done a PhD under the guidance of our principal sir. And during that tenure, during her research, our principal sir, along with Lavanya madam, actually has published a patent in 2018, and which got granted now in 2026. And we want to unveil the patent now. Choose my second page. And Sangeeta was my third page student. Next year, Padmini is my fourth, and Srikanth is my fifth. Srikanth left the organization. Yeah, first year, he has done PhD and of course, all from AU, but now he is working in libraries. Good morning. చెప్తాను ఒక ఫైన్ ఓకే ఓకే